we need them installed on the lab machines or an APK or whatever the heck that iPhone uses. We need those submitted, and then we need the desktop games installed in the lab machines. If you want your game to be featured on the website with a picture and a description, please contact Robbie for the additional requirements that you need to give him for that to work. Also, be sure to write up an extremely simple and comprehensive README file if you do want your game to be heavily featured on the site, because we are hoping to have more people be downloading these things. Also, if you'd like to be featured in the expo, please contact management, because expo is coming up, and if you'd like your game to be playable at the expo, we need to know very soon. Next is Amazon Game Studios is giving a presentation to Husky Games. There will be a little bit more on that a little bit later. Next week will be the management candidate presentation, so be sure to attend that. And we're changing the way we're doing attendance, which is why you all had to come up to Robbie today. Reminders, it was essentially just work on your games. You got around 2 weeks left to actually do any like real development. It's crunch time. Get on it. So attendance. Attendance was, for lack of a better word, less than stellar last week. The problem was that when we counted the attendance sheet and how many people were actually here, there were about 20 people who were here, who were signed in that were not here. This technically could be considered a breach of academic integrity, which could have consequences ranging from failing class to straight up expulsion. We're not going to pursue that because we can't technically prove who wasn't here and who wasn't, but you know, it's still something to take into consideration when you're doing these kind of things. I know most of you here are probably the people who come and stay for the whole time and listen to me yabber on about whatever, and I thank you. I'm just saying, if you know people who are doing this, you should probably warn them. We will be throwing out the attendance grade for last week, so that's a lucky break for some people. That won't happen again. Just a quick note, if you can't make it or you need to miss the meeting, all you need to do is email management. We are way more lenient than we really should be. So that's all it ever takes. Another thing is leaving in the middle of a presentation without emailing management before or even after without an excuse is unacceptable, and we will just count that as an absence from here on out. And then finally, we will be doing the card slider from here on out, so be sure to bring your IDs. Finally, the Amazon Game Studios and the final presentations. We have been contacted by Amazon Game Studios, which is pretty cool. They would like to give a presentation to our enterprise, possibly even take some resumes. So if you guys are interested, please send whatever updates you've made to your resumes, you know, since the career fair to us, and we'll probably put those together and try to get them over to them. However, they can only do it during the last week before finals, week 15. So we typically do final presentations then, right? Well, we got to make a choice, and I'd like to make this choice as an enterprise, so we'll have everybody vote. We have at least 5 volunteer teams, you know, volunteer to go the week before, the April 13th. These videos will probably be featured at the expo booth because you'll need to get them in a lot sooner. Otherwise, our meeting can go long on week 15. So who's all for option A? Who wants option B?
You got to vote for one.
Yeah,
and you got to have your hands high so we can see.
Yeah, that this half hand isn't working. So again, option A, please. Option B. You really want to stay here an extra like 45 minutes the week before finals week. All right. Okay, so plan on sticking around longer than 6 o'clock finals week. Yeah, and then quick games you might not have tried, which I'm not actually going to go through, but basically we got Quadrilateral Cowboy. You write bash scripts to commit heists. If you haven't played this, I definitely recommend giving it a look because it's extremely entertaining. I feel like you would like this particularly, Dr. Poole. Arma 3, this has been something of a real fun game for me and my friends. We can go into it later. I just have some funny stories from it. And then The Witness, it's a game I can't really entirely recommend, but it's extremely It's got extremely intuitive puzzle mechanics, so if you're interested in designing puzzles, this is a game to play. Anyway, here's Mitch. In all of his glory. Go.
Can you guys hear me?
Yeah.
Cool. All right, I'm going to start. I'll share my screen. I'll run through this all. Let's see, this looks like a good screen. Can all see the slide?
Yep.
Cool. All right. So for those of you guys that don't know me, I'm Mitch. I used to be the president for Husky Games. Before that, I was the VP of Ops. So I've really done my time in the prison that you're in right now. Just kidding. So things that I like to do is I do a lot of really weird things. I do a lot of video game programming on the side still as a hobby. I also have been tinkering around with like robotics and stuff. I currently work at Epic. I'm at work right now, so I have my own office, which is nice. So I can do presentations like this. I just graduated last spring, and now I'm already back giving a presentation. So the idea for this presentation came up just because I was making a game, and then I realized that there were a lot of really weird scenarios that I should probably address. But a lot of them are going to be very interactive. It doesn't matter if you actually say the answer, but you really need to think things through. Through questions throughout this whole thing just to make sure that you're engaged and I'm not just yelling at you, even though I can't see you. But there's also a link at the top. You see that little like Google Slides 9SM BTR. If you go to that, if you have a laptop or a phone right now, someone should go to that right now so I can make sure that they actually pop up on my other screen. Just say something. But if you have any questions throughout the whole thing, I think you can like upvote them and downvote them. And if something gets enough upvotes, I'll stop what I'm doing and answer it. So that's where the link is. It'll be up there for the whole presentation. I can't really see what you're doing, so this slide is bad. It's bad, Mitch. All right, so big picture, what we're going to cover. I'm covering three main things. One is what is an MMO. This whole presentation is called Concurrency for MMOs, and I was always a huge fan of staying away from buzzwords in the game of or in the world of video games, because there's a lot of people that do know what everything means, but there's also a lot of people that don't. So I'll cover what that is. Then I'm going to go into networking, because before you can do any multiplayer games, you have to know how to do some networking. And then the fun stuff comes in with concurrency. One of the biggest things that I think about for MMOs is RuneScape. And an MMO is a massively multiplayer online game. So there's going to be tons of people playing on one world, on one area together. But for the sake of this presentation, a game that you might have played is Minecraft. So it's not technically an MMO. A lot of people would correct me on that. However, the stuff that I'm going to touch on is going to be very similar between the two. So if you've played either one of these two, keep that in mind when I'm doing these examples. So I'm going to run through two of the most common type of multiplayer games that I see out there. The first one is something like Halo and Call of Duty. That's a matchmaking style game. And this is where you have your server, but it's not going to be doing all of the heavy lifting. Each one of these little controllers at the bottom is going to represent a player, and then I've got those gears to represent the server. So the server tells all the clients, all the games, the players about each other, and then they break off and do their own thing. That usually involves one being the host. But anyway, the server is not doing a whole lot other than setting things up. Here's the next little diagram. So there's 6 players, they're all doing their own thing, and then they report back to the server when they're done. Another type is something like this, where you have a bunch of players all connected to one server. This is you hit your limit of how many people can play at once. So you can do matchmaking. You can have tons of people playing because they're not constantly demanding the server's time. But if you have something like this, you're all demanding a fraction of that time. So here's your first little question. You got the little smiley face up there in the top right there, which means that you have to participate. Test question has 2 upvotes, by the way. So for a massively multiplayer online game where you have hundreds, maybe thousands of people playing, what type of server architecture do you think that's going to be? Matchmaking or server host?
Server host.
Oh, wow, I can hear you guys. You got it right. So it's a happy face. All right, so now you know what an MMO is. We're going to get into networking. Most of this is going to be real-time communication because we're not playing games like strategy games or online poker things or whatnot. Time matters. The game that I made, I think I showed on the next slide. Hey, there it is. So I made a little game. I like to do retro pixel art style stuff. But this is what I'm going to be using as an example throughout the whole thing. And it is real time, meaning that when you move, you want to see it move in someone else's player. It's also more real time than something like RuneScape, if you keep that in mind. So the idea with networking is pretend that you're sitting next to a blind person and you have to describe what you see on the screen. You have to do that through talking somehow. So the client, who is going to be the player, is going to tell the server what happened. The server is going to make those changes and then tell the client what they should see. And that happens over and over and over again. So with that said, for this example, just kind of think, it's got a little happy face here, which means it's another question for you to participate in. What does the server need to tell the client in order to portray this image? So once again, imagine that you're sitting next to someone who's blind and you have to describe this image to them. Think about all the things perfectly. You can't just say there's a nice happy picture with video game stuff in it. That's not good enough. You have to be very specific. So looking through here, even though it's a very small zoomed in screen, there's still a lot of information going on. So one of the first things is like the tiles. Top left corner is grass. The next one next to it, the flower. The next one after that's water, then water, then water, then grass. And then you kind of like flow on through that. So even just saying what the tiles are is very tedious. Also, if there's things that can be overlapping on things. So like there's a player on a grass tile. Now, going back to what I said earlier, how they're constantly talking back and forth, you don't want to be saying this all the time because then you're going to exhaust your communication. The concept of deltas come in. So this is something that the reason I actually started making this game was because I was doing some work at Epic, and we do all of our communication through deltas because you don't want to have to send tons of information all at once. So I decided I would make a game that used these as well. So the difference between this is instead of sending everything back and forth every single time, you just say what's new, what's changed. Player would say, hey, I moved. I am now at a different position. The server then updates them by saying, everything is the same from what you knew about last, except now there's a ghost that was near you and he's gone now. So the client will delete that and then keep updating back and forth. And even if nothing happens, the client still says, hey, nothing happened. It tells the server to let it know. So it's kind of, I didn't move. So this is a lot shorter than before. There's a lot of pros and cons to this approach, and it's really good for an MMO though. So the pros is much shorter messages, and we're talking a lot shorter. You're sending just a little bit of information. I guess you can't see the hand gestures I'm making here. And that really reduces your network traffic, and that's your real bottleneck between having a nice server going on, is how many people can connect over the network. It's usually not how fast your server is. It's usually how much information it can push through the wire. The cons, these are kind of like fake cons because there are ways to minimize these. But in order for you to do a delta approach, the server has to know what the client is like. You can't just say something's changed because you have to know as the server what the client has. So that way you can tell what is different to be able to send what's different. There are ways to minimize that, but it does have a little bit more memory usage. So I'm going to touch on two different types of servers that are easy for MMOs. The first one is the easiest one to implement as a programmer. These are synchronous servers. So a synchronous server just means that it does things in a step-by-step approach. It does one thing, it moves on to the next. There's no multiple things happening at the exact same time. It's very easy to visualize. Put this here, if the server has those gears, you have each player waiting in line. The server is going to talk to the first one in line, and it's going to help them with whatever they're talking to. The only problem with this is now if you have an MMO, which is not just a multiplayer game, but a massively multiplayer online game, you might have thousands of people waiting in line. And that's not going to be very good because now every single person is waiting for everyone in front of them before they can get their next little update. And if you want to update things multiple times every second, that's just not going to cut it. So what can we do to handle more players? Okay. So this is where this is the meat of the presentation now. And this is going to get into concurrency itself. So in order to avoid that line, we have to find a way to make the server be able to do more at once without having to wait for everyone or having everyone wait for the server. In order to do this though, I'm going to be touching on the parts of concurrency that matter to an online game. I'm not going to cover everything, and As all of you know that have taken concurrent programming, there's a lot to touch up on, so I'm just going to touch on some very high-level stuff here. Quick, and there are some things that I'm going to say that aren't completely true, but just kind of ignore them. If there's something that you hear me say that is like flat out wrong, though, if I accidentally say something, that would be your time to post something up in the questions so I can address it. Same thing goes, this is also going to get very technical. So if I say something and I just make an assumption that you know it, this is your time to click on that little thing or type in that URL at the top and post a question so I can slow down and go back over something. All right, here's the smiley face. So use your brain one more time. This is a programming question, very difficult here. You start out and your I is equal to 0, and I execute this line of code twice on just a regular program. If I were to type this into Eclipse or C or anything like that, what would I be after you execute this twice? Someone shout it out. 2, yes, that is it. So now we're going to make it a little bit more complicated because it's not going to always be 2 if we do something else. So threads are what are going to make this program run faster. And what it does is it allows us to run more than one brain on the same set of data. The same memory space is what that is. The memory space is going to be where all of your variables sit. So like I, when we're incrementing I is going to be in that memory space. The threads usually run on your processor on different cores. But once again, that can be abstracted depending on how your computer is set up, and there's a lot of simulations that go on. But for the most part, just think of them as completely separate processors. One thing I do want to point out is everything that I'm going to point out here is going to be more or less scary. It's going to show how your stuff can break. But if you are just doing a regular program and you've never explicitly said, like, I want a new thread, then your program is probably single-threaded and you don't have to worry about any of this scary stuff. So going into multi-threading is we're going to we'll treat it as multiple processors or multiple thinkers. So since most computers have more than one core or processors, we can split the work up to get it done faster, which is really nice. However, this is very dangerous if you're not thinking about it the whole time. You can't just simply take a program that you have that's running slow and have 8 processors and run it 8 times as fast. That's not quite how this works. You do have to do a lot of hoop jumping as a programmer in order for this to work. So let's take a look at what I++ is really doing. This is something that's straight out of Michigan Tech's concurrent class. So tell CK I'm stealing his material. So we've got I, which is being loaded from the RAM memory. The RAM memory is where your program is lying. So when I say that I starts off as 0, the first instruction that it has to do is your processor has to go talk to your RAM memory, get that information out of it. Then step 2 is we'll increase it. So now we know its value of 2, but it's still on, and we haven't stored it yet. So then the very last step is to actually save it back to that RAM. The reason that this matters, I guess I'll touch on that in a sec. I have a little animation. So we've got our RAM memory over there on the right-hand side with I equal to 0, and our processor's on the left. So that's step 1, we're loading I. It is 0. We know its value is 0. Then step 2 is to increase it to 1. And step 3 is to save it back. And that is the whole idea. That is every time that you do I++, that's what's really going on for the most part. So now for the example that I had earlier where you all answered 2, this is just happening the second time. We load 1, we increase it by 1, which is now 2, and then we store it back, and now the new value is 2. That was pretty simple, but now what happens if we have 2 threads running at the same time? And instead of doing I++ followed by another I++, we try to execute 2 at the exact same time. This is what's going to happen. So here's just one example. There's a lot of different orders, and your threads are not guaranteed to run at the exact same time, which makes it really tricky to predict what your computer is going to output. So if this happened, if your first processor loads I, which is 0, and then before it can do anything else, your second processor loads I, which is still 0. Then you jump back down and you have your first processor, increase it. Now keep in mind that you're increasing it from what the processor knows, not from what the RAM is. So it goes from 0 to 1. And then the second one does the exact same thing. The second processor had loaded 0, so it increases it to 1. And then each one will store 1 back to memory. So now even though you executed I++ twice, if you look back at what your memory is, the value is 1. And then the reason that this is a big issue is because depending on the order that they happen, is going to do two different things. So if you look on the left-hand side, I have computer 1 doing everything all at once, 2 doing everything, and then on the example on the right, I just switched 2 of the instructions, and that completely changes the result. You'll hear those being called race conditions. It's a good buzzword to remember for when you're standing in line at career fair, because that's one of those things that recruiters will check off the list to make you sound like you know what you're talking about, even if you don't. I don't think I even know what it is yet. So the reason that that's important, though, is because you can get undefined behavior depending on the order that your computer chooses to run things. So you have to know how it happens, or the technicalities of it. Like, for example, I++ was not probably something that you decided to break down into its most raw form. I don't expect you to decompile every single game code that you write down into its assembly and then mix them up to see if there's ever a difference thing. What we do need to know is that it is possible for things to happen. And if you're not careful, that you can get something that happens in 2 very different ways. So now it comes down to avoiding those race conditions. Race conditions are bad because then undefined behavior happens. One of the ways to handle that is with locks. So lock, I guess I will cover that here. A lock is to make sure that only one computer can run a chunk of code, or one processor or one thread, whatever you want to call it, can run some code at any given time. It makes sure that they can't get intertwined and run at the same time and mix up what the output is. I wrote my game in Java, so I'm covering how to do it in Java because it's a heck of a lot easier than it is to do in C or other languages. You can add this little keyword called synchronized function call. And what that will do is if you have multiple threads, only one of them is allowed to execute that at a time. If 2 of them try to execute it, one will wait until the other one finishes. So it's really actually pretty easy to do in Java. So now you might say everything is good because now we have code that executes and waits for each other. But if you think about it, now we're right back in the same situation that we started at. There's not a point of having multiple threads if we can't use them. So now comes into the complicated stuff. So the idea behind this is to get rid of our waiting line, or reduce our waiting line, I should say, and have each thread handle one player at a time. So that's kind of reduces our line by, instead of there being one bottleneck, we can have as many threads as our processor can handle, or server, I should say. The only downside to this is that each one of those threads has to do stuff a little bit different to make sure that you're not sending your players off with the wrong information. For example, let's just simplify this. We have a very simple server with only 2 players on, and there's going to be exactly 2 threads in it. So if the first one says, what enemies are near me, you would expect to get back a list of everything that's nearby. Now, the second one might say that they just killed one of the enemies. They killed a slime. And they're both talking to 2 separate threads at the exact same time. So keep in mind that they all are using this shared memory. So on the right-hand side, I just have an example of what the game state might be like. So you've got 4 enemies in the game. You got 3 players. You got a bunch of items. So that's kind of remembering the game state. That is the world being saved. So now each one of those tasks might happen at the exact same time. So now I don't expect you to come up with a single answer on this because it is concurrency. So there's a lot of different ways that stuff can happen, but I have the little frowny face there, which means that you really have to think today. So if player 1 asks for all of the enemies and player 2 simultaneously says to delete the slime from the enemy list, what do you think you can get? These are the 3 answers I came up with. So the first one, there's a chance that player 1 gets the list before player 2 even gets the chance to delete the slime, which in that case, they get all 4 enemies back, which is fine. That doesn't really matter. They're slightly behind because at that instance, that slime should be gone, but it's not. But that doesn't matter because your game is typically talking back and forth to the server many times per second, so it won't make a big difference if your game is 1/10 of a second behind. Possibility 2 might have been that the second player actually got their slime delete request in before the first player got that list back. So in that case, it's going to have the list of all the enemies without the slime, and that's the best case scenario. But possibility 3 is not what we want at all. this, and I will explain how this can happen. If you look at it, there were 4 enemies, and we said to delete the slime, but instead of getting a list back without the slime, it gets one back without the ghost instead. And that is really bad, because now one of your players has a wrong state of the game. That is not how the game is supposed to be. A ghost just disappeared, but the slime that should be dead is still there. So 1 and 2, they make sense. But how did question 3 happen? Just put on your thinking cap. I'll walk over this. Okay, so thread 1, its goal is to look at all of the enemies. And what we're going to do is we're going to loop over every single thing in that list, and we're going to build a response. And we're going to get ready to send. You can think of it as writing a letter to player 1 on snail mail, and then we're going to send it through the mail. Thread 2, which is coming from player 2, is at the exact same time trying to find and delete that slime object. So thread 1 on its own, this is what happens. We've got a response on the left-hand side. It's like snail mail. We're going to write a letter. So what we're going to do is we're going to move to the first slot, add the enemy to the response, move to the next, add it to the response. And that's kind of how we're doing it. We're looping over. So this is an array. You can kind of see a little animation. We look there, we add it. Next thing we do is we look at the slime and we add it. Then we look at the ghost and we add it, and the spider and we add it. So now we finished our list, we looped over all of the items, so we send back the message to the player. So that was the simplest version. All right, now we're going to throw in thread 2. They're not guaranteed to run in any order. It's going to come in at a random time. So let's say that this scenario happens. We get the goblin, then we move over to the slime. Now we have our thread 2, which comes in and it says, my job is to kill the slime. So it comes in there and it deletes that slime. Well, what happens as part of the deletion now is, let's say that it shifts everything back over. Now what happens is, if you look at our response, we already added the slime and it's not there. But then the next time that we loop over here, if we go back to thread 1, is we already looked at that spot, so we skip it and we move on to that next one. And now we completely missed over that ghost, because the ghost should be where that spider is, but instead everything shifted over, which means it shifted out of our looking range. So to go back to that, so now it sees that it hit the end of the list, and that's why it sends back this incorrect list. So that's one of the really weird cases. So now it comes down to, how can you fix it? This is actually the stuff that I was working on for the most part. So I've seen a lot of games. I keep using RuneScape as an example because I like to look through a lot of their stuff. RuneScape is a pretty old game, and they handle a lot of these concurrency issues pretty well. However, they do a lot of locks. They do this very top one here, locking sensitive memory. And I will touch on each one of these 3 things. Another thing is called a fixed memory model, which is something that Minecraft does. And then the very last thing, which is something I did and very few people out there actually do, is using thread-safe data structures, because they're kind of complicated. So method 1, locking sensitive memory. Oh, performance. It's not good performance, and that's kind of a big thing. So keep that in mind while I'm doing this, is ask yourself, why is this not good? So going back to our example here, where it's asking what enemies are near me and the ones killing a slime, what we're going to do is we're going to do what I said with that synchronize thing, and we're going to lock down that enemy section. So step 1 here is to say, I'm going to lock this. As soon as you lock it, everything else has to wait. So now as soon as process 2 tries to execute, it gets a wait instruction. It just says, hey, hold on 1 sec, someone else is using this memory. So we're going to wait. As soon as this one is finished, then this one is allowed to claim that lock as well, and then delete the slime and execute. Oh, I meant to do that slide there. So locking it, make sure that you're not having 2 things manipulating the same space at the same time. However, here's like a really dumb question though, is how often do you think clients are going to be asking about the entities around them? Well, the answer is going to be all the time, because as part of a game, every, let's say, 1/10 of a second, you want to know what the world is like in order to have a real-time game. So that actually happens quite often, which means that it's really bad to be locking that memory, because now, once again, everyone is waiting on you to finish, and it destroys the whole concept of having these multi-threads. So yeah, if we lock every single time that a player wants something, we're right back to the synchronous server. So even though we have multiple threads and we complicated it like that, we're really bottlenecking it in the same way. We're all waiting on one specific resource. Which brings into the fixed memory model. This is what Minecraft does. This is better performance, but in terms of flexibility, meaning like how big you can expand your game, it's actually not so good. It really limits the size of your game. So a fixed memory model, what you do is you pre-allocate space, meaning that you decide up front, what is the most number of something I'm ever going to ever need? And that's your fixed size. So what happens with this, though, is now you do not shift when you're deleting things. This is what Minecraft does, is if you actually pull up the source code, I don't think it's in the source code. I think it's just in the settings file for it. There's a spot where it'll say the max number of enemies, the max number of items, the max number of everything. And you can specify what those are. So when you delete something, you don't shift. You just leave a hole there. But the really nice part about that is now you can have something reading at the exact same time that you're deleting, and it won't corrupt your data. The pros is that you can modify it concurrently. You can do different things at the same time. But the bad thing is that it leaves gaps in there. So one of the things that is actually really fun to do is if you do play Minecraft, jump in there and set the maximum number of something, the maximum number of enemies, to be something really, really, really high. So even if there aren't that many enemies in the game, your game will run slower. And the reason for that is now you have tons of gaps. And every time that you want to ask where all of the enemies are, it has to loop over all of those empty gaps and check, is there something there? If there is, it'll send you information back. So once again, the larger your allocation is, the slower it is. However, this is a very performant model if you know the maximum number and you can be very confident in it. But if you're just trying to set it to some arbitrary big number, then you're going to have some performance hits. Hey, look at that. Fixed memory model. So once again, there's a max number of players, there's a max number of animals, there's a max number of monsters, a whole lot of things like that. But that's a very popular game that uses that model. Method 2.5, I guess, is the fixed entity model. This has much better performance, but you cannot be flexible in it. And this is actually a really creative thing here. So what happens here is you never actually delete things. You just mark them as deleted. So this is, if you've played RuneScape and you chop down a tree, the tree itself does not disappear. It just gets chopped down and maybe 30 seconds later it reappears. This is what they're doing here for that, is they're just marking it as hidden, deleted, destroyed, or whatever. But what happens is one entity will always be in that exact same place. It will always be that one thing forever. Example for this. Oh, look at that. I have screenshots. I forgot. So yeah, this is what happens in RuneScape, is if you chop down a tree, it leaves a stump there for a little while, and then it comes back. So it didn't really delete the tree and create a stump. It simply changed the tree's state to the bad part about this, though, the reason I say flexibility is because once something exists, it always will exist there. You can't just spontaneously decide, hey, I want to have a duck next to me. You can't just randomly create another duck. That duck had to be predetermined to exist in this game, so that way you could enable it. You enable and disable things instead of actually creating and destroying things. So method 3 here is the thread safe data structures. Performance is fantastic. You have lots of flexibility. However, it is going to require a lot out of the programmer. So what this is to try, you really have to analyze your game. There is not just a simple one-off solution for everything. You want to make sure that your data structure that you're doing makes sense with your game. All right, so what I'm going to do here is I'm going to get rid of the idea of just having like an array or a list of something, and I'm going to create something very similar to a linked list to start. The idea behind this is if you look at any one object or enemy in your game, after it, and it points to that enemy after it, and that one has something that points to something after it until you eventually hit the end. So let's just start with this and do some simulations here. For reading, there is no lock required, meaning that you can just start at the beginning and just say jump to the next and jump to the next and jump to the next until you eventually hit the end. However, this is not good because if you want to add or delete things, you will need a lock. And I think I have this in here. Yep. So is to delete. I want to make sure my slides are right. All right, to delete, all we're really doing is adjusting a pointer here. So for example, our goblin is our very first entry in here. And if I wanted to delete the slime, like our example said, all you have to do is change the pointer from the goblin to point to our ghost. Now, what's really nice about this is if you think about it, if someone was looping over this, so let's say someone is reading over it at the exact same time that we're deleting this, and we started at the goblin and moved over to the slime, and then I immediately delete the slime, it doesn't break our iteration because I can still be at the slime and say, what's the next object? And it will give me the ghost. You can have multiple things pointing to things, but one thing can only point at one other thing, if I said that right. Something can be pointed at from different things, but you can only point to one thing. So that's really nice for deleting because you're all set. So the pro on that is it's a very linked list style structure. It's always safe to read, which is really nice because keep in mind for a game, people are always asking, well, what's like reading is your most important thing. The only con to this is it's very slow if you want to find something very specific. So for example, if I say I want to find the third entity, you have to start at the very beginning and jump 3 hops. So I actually use this data structure here in my game. And these are very old screenshots of the game because I did this when I was originally going to do this presentation, and then I did another month's worth of development after it. It's a little bit further ahead. So now that you understand where concurrency comes from, I guess, what are you supposed to do it with? This is something that I cannot stress enough is you really want to try it out. It's something that I would really suggest doing as like a hobby game, but do not do this for Husky games. I cannot recommend staying away from concurrent multiplayer games as much. Like this took me a very, very long time. I used to come home, I'd work on this for 6 hours a night before I'd go to bed, and it took me a month to make this game. And you're going to look at it, and it's going to be pretty simple. And if you were to do a single player game with the same mechanics, it would take you not as long. So I guess I have the source if you guys are interested in it. It looks like I have no questions here, so I don't have too much to answer right now. I do have a GitHub account. It's on there. The game is, I don't know if I said what it was called. Yeah, it's called Brandon Shaved Yesterday. I don't know if you guys are familiar with Brandon Kuknicki, but he was also in Husky Games Management. He works with me, and after work, we go home and make video games because we're boring. But anyway, the URL is github.com/my username. It's the Cakester with a K. And you'll see the little game right there, Brandon Shaved Yesterday. That is it. That's what happens when you ask him to name games. There's installation instructions. It's actually pretty easy to set up. I say that because I made the game. So I guess it comes down to a demo. So this is not so much of a demo as much as I wanted to test how many people can play this game at once. I'm not sure how many of you guys brought your laptop since I can't see you, but I'll be interested to see how that works.
6, 7. I
am on the game.
9 right now, Mitch.
There's 9 people on?
No, but there's only, I think it's only me that's logged into the server right now.
Okay. So there should be a URL that Zach has. Zach, can you tell me what that is?
It's on the chalkboard. It's 141.219.236.56. Yeah, you can log into it on your phone. You can't do anything, but you can at least log in. I see people.
Yep. Let's see. Present. I should.
4 players online.
All right. So this is the game. If you guys can see on my screen, I'll try to make it a little bit bigger. Roll. I guess I can't roll. So let's see if we can see anyone else running around. My code actually works here. I'm in the game? Am I in the game? That's the question. I'd have restarted. I feel like I see people. Oh, someone's telling me. There's a whole lot of stuff that can go on in this, and you're more than welcome. My game is open source. I like how everyone's killing each other. All right, I'm getting out of there. It is a multiplayer game, and it's kind of interesting how by learning how to type. It's pretty interesting to see how this works. It's a very hard game. If anyone can beat it, congratulations. After you walk through the tutorial island, you're all set. The reason that we made the game the way that we did was we tried playing it, and if we could run through it in one go without dying, then we restarted it, and we made it harder, and we put more enemies in it and whatnot. It's a giant world. Give it a shot. If you die, you turn into a zombie, and the zombie kills people. If you log out, your body becomes a zombie, and the zombie kills people. So, quick. Oop. Oh, I died. Oh, I didn't.
By the way,
does anyone have any questions? Let me pull that question link back up. Present from beginning with present.
So just a quick poll, how many of you are actually logged in right now? Okay, a lot. I don't know, can you query how many people are?
It jumps up and tells me when people join. But people keep killing me.
All right, everybody, be nice. Quit killing Zach.
19 players.
For the question. So if anyone has a question, go ahead and type it in, or just yell it out. I might be able to hear you.
How do you get out of the first room?
Good luck. Hey, check this out. You ready? If you guys can see my screen.
Yes.
Be a cheap way to get out of the room.
Fortunately, I actually am somewhat. Why can't we use those hotkeys?
This is where we use a business called cheese.
Someone keeps the text. Why do you keep
So,
Someone asked you something? Because I have very bad feedback.
I did. So if any of us find any bugs in your game, we're allowed to post them to your GitHub issues, right?
Yep, I actually do go through and answer those. So.
Okay, so if you find any bugs, like the sign keeps killing you, possibly post it to GitHub.
Yeah, there's people spawning. When you spawn, you hit the space button, and the space button kills people around you. So.
Oh, zombies! Ah! Darn it.
Anyway, so before we all stop paying attention, does anyone have any questions for Mitch?
Oh, someone asked, where do I access the microtransactions in your game?
We actually got denied for microtransactions. I was upset about it. We applied. Google was not happy because our server was not online 100% of the time because we were debugging it. So they did our little polls.
Any other questions for Mitch?
This is a very suspicious thought.
How do I get out of the first room? Pray that nobody's blocking the door.
Do you have anything else, Mitch?
No, that would be everything. So the only recommendation that I have is if you guys, whoa, wow. All right. If you guys are working on a concurrent game, let me know because I'm interested in it. Oh, also, the fun thing about this game, the reason I wanted to do it was because if you notice, you didn't have to download anything. It was 100% JavaScript, which was kind of fun. So the server hosts it, and there's nothing fancy that you have to download because usually when you make a multiplayer game, you have to do some sort of communication. So the behind the scenes is kind of scary of this, how it communicates. It does a lot of requests back and forth, but if you guys are interested in learning how that works, you can also reach out to me and I'll run you through it.
Okay, cool. Everybody give Mitch a hand.
All righty. See ya.
Bye.
Bye.